October 2024. SpaceX catches a super heavy booster for the first time. And honestly, the whole world lost its mind for a moment. But then engineers started reviewing the slow-motion footage, and they spotted something. Those massive chopsticks, they didn't just stop cleanly, they bounced back after making contact, flexing like your car's suspension when you hit a pothole too hard. Now, for Super Heavy, with its thick stainless steel body, that's not really a problem. But Starship's a different story. We're talking about 18,000 ceramic tiles that can survive 1400 degrees Celsius, but crack if you look at them wrong. So here's the question that must have kept SpaceX engineers up at night. How do you fix a 120-meter tower when you only discovered the problem after your first successful catch? Let's go back to that moment. Booster 12 is coming down towards Starbase, and those chopsticks close around it at exactly the right time. Perfect catch. Engines cut. SpaceX just pulled off something most people thought was 5 years away, minimum. But when the high-speed camera footage came back, engineers noticed the chopsticks flexed under the impact. They bent slightly, then snapped back. Classic rebound effect. Think about slamming on your brakes in a car. Your body lurches forward, then rocks back as the suspension rebounds. Same physics, just scaled up to 120-meter steel arms, stopping a 250-ton booster falling from the sky. For Super Heavy, this wasn't a deal-breaker. The booster's built tough, thick stainless steel construction that can take a hit. SpaceX knew there'd be some flex in the system and designed accordingly. But watching that footage, someone must have asked, what happens when we try this with something that's not built like a tank? And that's where things get complicated fast. Super Heavy's flight profile is pretty straightforward. Up for about 3.5 minutes, peaks around 70 kilometers, then comes straight back down. Quick turnaround, stays close to home. Starship? Completely different beast. It's going to orbit, hitting speeds of 28,000 kilometers per hour. Could be up there for hours, maybe days, just circling Earth until the landing site rotates back underneath. The whole time it's exposed to the space environment. But re-entry is where the real violence happens. When Starship hits the atmosphere at orbital velocity, the physics get brutal. Air compresses so hard in front of the vehicle, it ionizes into plasma. The windward surface heats up past 1,400 degrees Celsius. We're talking temperatures that would melt most metals into puddles. That's why those 18,000 ceramic tiles exist. Each one is custom-shaped, precisely positioned. And here's the thing about these tiles. They're remarkable at handling heat, but terrible at handling mechanical shock. Each tile costs maybe $10 to $20 to make, which sounds cheap, until you realize the real expense is installation time and the fact that they're fragile as hell. Strong under thermal load, vulnerable to any kind of impact or lateral force. If the chopsticks bounce even a little during a Starship catch, tiles near the contact points are going to crack, maybe shatter. And once you've got damaged tiles, rapid reusability goes out the window. You're looking at inspecting all 18,000, pulling off the broken ones, installing replacements, verification testing. That's weeks, possibly months of work. So SpaceX had a real problem. The system that worked great for catching boosters wouldn't work for the upper stage, not without changes. They had two options, really. Option 1, throw software at the problem. build incredibly sophisticated control algorithms that predict and counteract the rebound in real time. Kind of like how you might ease off the brake pedal slightly just before your car comes to a complete stop, reduces that final lurch. Sounds good in theory, but predicting how 120-meter steel arms will flex under dynamic loading? That's a nightmare calculation. You need to model elastic deformation on the fly, account for wind, factor in the exact weight and descent rate of whatever you're catching, then adjust in milliseconds. It's doable, technically, but you're adding massive complexity to a system that needs to work every single time. And complexity means more things that can fail. Option 2 was, well, honestly, kind of obvious once you think about it. Don't make the software more complicated. Make the hardware simpler. This is where Pad 2's design gets interesting. SpaceX cut 10 meters off each chopstick arm, just made them shorter. The physics is basic. Less mass means less momentum, which means less force to absorb when you stop, which means less rebound. Simple. But they didn't stop there. Pad 2's chopsticks are also way more reinforced than Pad 1's. Heavier structural members, more bracing. The arms are stiffer, so when they move, they flex less under load. You've basically transformed the whole catching mechanism from something that needs incredible software finesse into something that's just inherently more predictable. There's another benefit that's easy to overlook. Shorter, lighter arms? They respond faster. During those final seconds when Starship's drifting toward the tower at maybe a couple meters per second, you need to make tiny adjustments to match position exactly. Lighter arms give you that agility. Cutting the chopsticks short wasn't a standalone fix, though. It triggered this whole cascade of design changes. Most obvious one, if your arms are 10 meters shorter, you need to make the tower base taller. Otherwise, you can't reach high enough to catch anything. And we're not just talking about stacking more metal. You need to maintain structural strength for the forces involved. Pad 2's base is built fundamentally different from Pad 1. Instead of a concrete core wrapped in stainless steel, they went with a stainless steel framework filled with concrete. It's a stronger, more rigid approach. Has to be, because this tower needs to handle not just current Starship variants, but also Block 3 vehicles down the line, plus the rapid launch tempo SpaceX is planning. And when they say rapid launch cadence, they're not talking monthly. Eventually, they want weekly launches from the same pad, maybe daily. Each catch puts serious stress on the structure. You're stopping hundreds of tons descending at several meters per second. Do that dozens or hundreds of times, and any design weakness is going to show up fast. The catch pins on Starship had to be repositioned too. They need to line up perfectly with where the shorter chopsticks close. Get the height wrong, too high, arms can't reach. Too low, you're putting weird stress on the vehicle's structure. During Flight 6, SpaceX actually tested leaving heat shield tiles off in the catch pin areas. The exposed metal survived reentry just fine, which validated their plan to just remove tiles where contact happens instead of trying to protect them. What really strikes me about Pad 2, though, is how it sets up everything that comes next. Once you can catch both stages at the same tower reliably, the whole operation becomes streamlined. Booster comes back, gets caught, inspected, refueled. Ship returns from orbit hours or days later, lands on the same tower, goes through its own prep. Everything's in one place. Less infrastructure, less logistics complexity. That's the real breakthrough here, not just catching rockets, but building an operational model that actually scales. So that's SpaceX's real superpower right there, learning from what works. That first booster catch revealed a problem nobody anticipated. The solution? Cut 10 meters, reinforce everything, trust hardware over software complexity. Those shorter chopsticks aren't just about catching Starship safely. They unlock orbital refueling, rapid reusability, Mars missions. Everything downstream depends on this working. Flights 13 through 15 are going to tell us if they got it right. If you found this useful, subscribe to New Space Review. We dig into the technical details other channels skip over. We're all watching this history unfold together, and I want to keep you updated as it happens. Before you go, check out the video on screen about Elon's plan to actually live inside Starship's fuel tanks during Mars transit. Yeah, seriously. Click through, it's wild.